Welcome everybody to the lectures of week 5, and we're going to start with a bit on stability, where we tie in the concepts of stability you've learned in block 4 in the first year to the stability properties we will be discussing in control theory. Now, so we'll build up this lecture series where we'll talk about, well, automated flight in practice, where we'll later show you some step responses. So if we have a step as an input, we'll see what the response of a system is and tie that into different properties of a mass spring damper. We'll talk about block diagrams, a bit about control theory and stability of systems, where we now start with stability of aircraft and then of control systems. So the question is, well, what is stability? Everybody has this notion of what is stability, but we'll have to formalize this. And in aviation specifically, also in other fields, we can also discern a static stability and dynamic stability. And we'll talk about these two next. So stability is the ability of an object or system to maintain its equilibrium position after displacement. And the one of the prime examples is, and we'll show that in a minute, if you have a ball and you have a ball in the center, if you perturb it, if you disturb it, it will slowly go back to the equilibrium position. And this is also something that we want in aircraft. But static stability is a very, very specific form of stability. It is the property of the system when it is displaced in a certain direction to return to the original state of equilibrium. So if you if a ball is moved, in this ball is moved sideways, it will first go back towards the bottom of the ball. And this is also the case. What we want in an aircraft is, if due to a gust or some turbulence or some accidental movement of the control column, a quick jolt, is that maybe the airplane rises a bit, but the initial tendency of the aircraft is to return to its original state of equilibrium. Its point where it used to be, where it was basically in a steady state. Now, so if something is perturbed, so it goes up, the initial return to its equilibrium, that tells us about, well, static stability, but it doesn't tell us anything about what will happen in time. Will it slowly damp out? Will it oscillate towards its equilibrium? Or will it become unstable and go completely out of control? So static stability tells us something about the initial tendency, and we'll need a different concept to tell us about what will happen over time. And so here we have the three classic examples of static stability, where we have a ball, and figure A, of course, is stable. If we perturb the ball in, let's see, at this point, hang on, no, you can't see that, at the point in the bottom, then the initial tendency of the ball will be to return to its equilibrium position at the bottom. Now, if we look at figure B, this system is not statically stable. If we move that ball just a little bit one way or the other, then it will keep on moving in the displaced direction and fall off this hill. We call that an unstable system. It's a static, unstable system. C is some kind of boundary situation where it's neither really stable or unstable, and it's called a neutral with respect to stability, and we very, very rarely see systems like that. But it is possible. If you move an object along a table, it will neither go back to its equilibrium position or go further away. It just displaces a little bit. So this is static stability. It's either stable, unstable, or neutral, where stable means it will return to its equilibrium position. Unstable, it will not. It will just simply go further away. And C is neutral or indifferent. And we can imagine that if we're in situation B, where a system is simply unstable, it is not going to, no matter how long it takes, it will not return back to its equilibrium position. And these are systems we want to try to avoid, especially in aviation. Now, static stability. So we have three options. So we have displaced this system from its equilibrium position of 0 up a bit. Now, if it continues to go upward in time, statically unstable. If it stays where it is, statically neutral. And if it returns back to the t-axis, it's called statically stable. But what are the options when we let time run? Then we talk about dynamic stability. This tells us what happens over time, especially over a large amount of time. Will it go back to its resting state or will it not? So it describes the change as a result of the displacement of the system out of its equilibrium position over time. Now, here we have a statically stable system because we see that it's been perturbed from 0 up to 1, but its initial response is to go back towards the equilibrium position. Now, in time, yes, it is going back, but it's oscillating with a constant amplitude. So it is not returning to its initial state over time. There's always going to be, it's always going to be at a point where it moves away from it again. And this is called, well, it's not moving further away. It's not coming any closer over time. This is called dynamically neutral. For example, purely sinusoidal, cosinusoidal function will be dynamically neutral. Yeah. Of course, in the next couple of slides, the equilibrium position will be at 0. And of course, that doesn't have to be the case. But for these examples, we'll put it at 0. Now, if we expand the cosine function in terms of two complex exponentials and a real exponential, we see that the exponent of the real exponential is 0, which means that if we let this over time, e to the power of 0 t is just 1. If the exponential is positive, it will have an exponential increase, and if it is negative, it will decrease slowly back to 0. And so this is some hint as to what will be required for dynamic stability. Now here you see a system where we've perturbed it again from its equilibrium position up a bit. We see it initially returns back to the towards the equilibrium position, but also if we look in time, we see oscillations, but they slowly dampen out, and we would call this a dynamically stable system, and of course statically stable. For example, if we take again some sinusoidal part where we see the two complex exponentials, but we also now see a real exponential with coefficient with exponent minus 0.1 t. So it's not very big, but it is negative, which means that the oscillations will slowly dampen out. And with a negative exponent, we will see a dynamically stable system. Now here we see a system where we've perturbed it, and initially it will go back to towards its equilibrium position, but the oscillations are getting bigger and bigger and bigger, which means it is by no means stable, and so even though it's statically stable, it is dynamically unstable. Now here we see the exponent is 0.1 t, it's a positive exponent, and then we see unstable behavior. Here we see a system where there are no oscillations. It's been perturbed, it goes back towards its equilibrium position, so it's statically stable, and over time it goes towards its equilibrium position and stays there, and so it's dynamically stable as well. This is, for example, what we see if we had a bowl, but we would fill it with oil. If we perturb the system, the ball will very slowly come back to the equilibrium position. And this is also something that is very important, because the oil is not just a randomly chosen example. It is a fluid that acts as damping. And damping is something we see a lot in especially physical systems. We've talked about mass spring damper systems, and so this could be seen as the damper part of our system. Now, if we talk about stability in control systems, what we mean with a stable control system is that over time it returns to our equilibrium position. And so there are a couple of examples of stable systems. One, it can go back to its equilibrium position while oscillating, but the oscillations have to dampen out, and that's in control theory what we call a stable system. And the other example is here, where we see just an exponential decay towards the equilibrium position, and it doesn't really matter how it gets there, but over time it has to get within a smaller and smaller and smaller bandwidth around that equilibrium position, and for t to infinity it should asymptotically reach this equilibrium position. And that is really what we talk about when we talk about stability in control systems. Now, in aviation, we make the distinction between statically and dynamically stable. There are also many other combinations which I won't go into at the moment, but for control systems we look at stability where we really look at dynamically stable systems, but their dynamically stable can only really exist if a system is statically stable. In the next video, or one of the next videos, we'll talk about a mass spring damper system, where we will also see the response of an initial condition. So if let's say a plane is perturbed by a gust of wind from below, its initial response will be to slowly level off and come back down. Doesn't mean it's dynamically unstable, but there's an initial vertical speed pushing it up. If we were able to just simply nudge it up higher, which in reality, of course, is impossible, then you would see an initial descent back to its equilibrium position. But of course, if we have an aircraft which is pushed up, it will just continue to go up, but the tendency will be to return to its equilibrium position if it is a stable system. So there we have the distinction between stability, which we talk about typically in aviation, and stability, which we typically talk about in control systems.